Welcome back to week 4 of the class Neuronal Dynamics. In lecture 1 of this week, I started a reduction of the Hodgkin-Huxley model, and to do so I exploited two observations. The first one is the dynamics of M, the gating variable M, is much faster than those of the other variables. The second observation is the dynamics of H and N, the two remaining gating variables, are very similar. And this is what we're going to discuss now in more detail. So here is the Hodgkin-Huxley equation. And as I've discussed in lecture 1 of this week, the dynamics of H and N are similar in the sense that if N goes up, H goes down. If H goes up, N goes down. Therefore, we have a mirror symmetry, which led us to say, well, 1 minus H is very similar to N of t with some constant A. And I would like to make this argument more precise now. So, let's look at the graph here on the right-hand side. At the beginning, the voltage here is at rest. I've chosen the voltage scale such that the resting potential is at 0. While the voltage is at rest, the activation variable N is at a certain value, and the inactivation variable H of the sodium current also takes a certain value. I can take the combination of those two, N and H, and plot them in the two-dimensional graph. Say here is my resting value of the two. So this is N rest. More precisely, it's N0 evaluated at U rest. Here is H rest. More precisely, it's H0 evaluated at the resting potential. Now this is one combination of N and H. Now at some point here at 20 milliseconds, a step current is switched on and the neuron starts to emit spikes. During the spikes, the H variable does some detours, the N variable also does some detours, and the two of them are sort of mirror images. For example, immediately after the onset of the stimulus, I see that H is going down. This might be this point here. Then, a little bit later, H has gone down even further. N has gone up even further. So this might be this point. A little bit later, H goes through a minimum. At the same moment, H goes through a maximum. And then they move down again, together. So at each moment in time, I can read out a combination N of t, H of t. For example, this might be the point N of t, H of t. And there are many points. I can evaluate this at each moment in time. I can take one of these samples and I will find many points in this two-dimensional plane. And each point is characterized by two coordinates, its value n and its value h, which gives the vertical axis. So during one of these spikes, n and h do some kind of movement in this two-dimensional coordinate space. If I give a different stimulus, the trajectories might be different. However, what you find is that all data points lie in close proximity to this red dashed line. There's a cloud of data points, and this cloud of data point does not fill the two-dimensional space equally. But this cloud of data points is elongated. And it has a preferred direction. And this preferred direction is given by the red dashed line. So the red dashed line represents the function 1 minus h equals a times n. So if n is 0, I'm here, then the red curve is at 1. More generally, this could be some arbitrary constant, some constant c. But for the sake of simplicity, I've put this constant to 1 so that it's easy to draw this line. So if h has a value of 0, then I'm at this point here, a times n equal to 1. Now any arbitrary data point, like this point down out here, can be described by the two coordinates n and h. This is the coordinate system that is sitting here at the origin, and this is the direction of the n variable, this is the direction of the h variable. However, I could choose a completely different coordinate system. For example, I could say, well, given that the data cloud is elongated, I put my coordinate system with the origin here, and then I define my first axis in this direction and my second axis in this direction. And the same point that I have here can now be also expressed in this new coordinate system by its distance from this new origin along the red dashed line. That would be this value here. Let's call it w. W would be the location along the red dashed line, and z would be the second coordinate. So this is my first coordinate vector, and the second one is orthogonal to the first one. Now, any data point in a two-dimensional space can be expressed by two coordinates, and after change of the coordinate system, the values are different, but it's still the same point. Now, as we have seen, all the data points lie in a cloud of points that's elongated, and in fact, that's very close to this red line. So, this point here, for example, it will have a w coordinate given by the distance here, but its z value will be very small. So I can project a data point by keeping w, but putting the z value down to 0. I suppress my second coordinate because it's always small. And this is what gives the reduction of dimensionality. So here, again, the idea, an arbitrary point is projected onto, in this case, the solid line. It's projected, and its position along the solid line is represented by the vector E1 that corresponds to the biggest elongation of this data cloud. In general, this point here does not need to be 1. It could be some arbitrary constant c. And the question is, how do we get this slope? Well, it comes out of this elongation of the data cloud. But for the case of simplicity, let's assume we put this here at 1. Now, a simple way to determine the value A is to say, well, at least when the system is at rest, I have my n rest, that's this value, I have my h rest, that's this value. At least when the system is at rest, I don't want to make a mistake. So the resting point should lie on my straight line. At the same time, I know this point here, the line starts at 1, which means now I know 2 points. I know the upper point, and I know some other, the resting point, and therefore the slope is fixed. So at rest, I have the condition h0 of u rest equals a times n0 of u rest. I put this to the other side. I have n0 of u rest. And that would give me the slope parameter a once I fixed my constant c to 1. Okay, so this is how we can reduce the two-dimensional description in this two-dimensional plane to a one-dimensional coordinate that corresponds to the projection onto my green line. But what about the dynamics? We know that h likes to go towards h0 with some time constant tau h. N likes to go to n0 with some time constant tau n. Therefore, it's not surprising that we can reformulate a dynamics for the new variable w such that we say w likes to go to w0 with some effective time constant tau f. And with this, we have arrived at the end of the argument. We have, in the Hodgkin-Huxley equation, we have inserted the momentary value m0 of u. We have replaced h by 1 minus w. We have replaced n by w over a. And we have found an additional equation for this new equation w. W likes to go towards w0 with some time constant tau effective. Constructing this w0, constructing the time constant tau effective out of those two functions is not trivial. It's some additional calculation, but it is possible. So this is our final set of two equations. What I can do now is I can try to pull out a time constant. I multiply with r, where r is 1 over GL. I multiply with the leak resistance. So I have here RC, and then I have here GNA times R times GK, and then R times GL will go away, R times I. And this is the membrane time constant tau that controls the dynamics of the voltage variable U. Let me do something similar for the W equation. I have here some effective time constant, say it looks like this, just a guess. Say here's my resting value, U rest. This turns out to be a typical value. So this would be the resting value, and I call this tau W. So let's multiply with tau W. Then I have here tau F divided by tau W. So this is a normalization factor, and the net result is that I can write my W equation with a time constant tau W, which is representative. It could be the resting value. It could also be the mean value of these different values that I see here. Some representative value of tau that controls the W dynamics On the right-hand side, I have the variables u and w. U comes in here and there, W comes in here. And I have my voltage equation, again with U and W. U is here and here and here and there, and W appears here and here. Now this is an explicit form. U is a variable which is time dependent. W is a variable which is time dependent. U is the variable, time dependent. W is a variable which is time dependent. However, it's convenient and normal to suppress the arguments in these functions f and g. U is the variable, you see it, because on the left-hand side you have the time derivative. And therefore, we arrive at a final set of two equations. The voltage variable is characterized by the membrane time constant tau and some function. And on the right-hand side, we have some function f of u and w. The w variable is characterized by a time constant tau w. And on the right-hand side, we have some arbitrary function g of u and w. With such a two-dimensional system of equations, we can do marvelous things. We can analyze the behavior of the neuron models. And this is the topic of the following few lectures. Please have a moment to look at the quiz.